Hi, I'm Albert Greenberg. I'm going to talk about some joint work with my colleagues in the research part of AT&T Labs, and this URL gives a paper. What we've been trying to do is come up with a set of systems and a toolkit that goes along with those systems that provides some sort of sound basis for traffic engineering in large ISP networks today. And we found that those same systems provide good infrastructure for a number of other tasks like configuration management. I ought to mention that this is also joint work with a lot of NANOG regulars from AT&T here, like Jay Borgenhagen. Whenever I see him out of New Jersey, I worry about our network. Let's see. But I guess we're all connected here, so we're okay. So what is traffic engineering about? It's got a very simple goal. We want to improve performance of the network, better matching the network resources to the demands. It sounds simple. Some of the drivers for this are, customers are asking for much more predictable quality service, reliability, and much better security, and that's being given teeth in service level agreements. There's growth in every dimension. That was symptomatic of the session this morning, where we're exhausting various kinds of resources. And when you look at the network, you see the link speeds going up. Just the number of routers, the number of links, the number of customers, the number of peering points. It's getting very difficult to keep track of everything. On top of that, do we have those resources in the right place? Well, probably not. It's not possible to know ahead of time where the big demands are going to come. So, basically, forecasting is not very good. On top of that, we have other services that want to ride on top of the IP network, voice on IP, VPN, provider-based VPN, to serve that kind of thing, multicast. This is not likely to simplify the network. So what do we do? Well, I think the industry is responding with higher capacity network elements and more easily configurable network elements, and they give us a large set of interdependent tuning parameters, some of which have been discussed all day, right? With respect to inter-domain routing, I think less attention has been paid to actually the supporting systems and tools that tell us how to use that improved infrastructure, and that's what this talks about. It's pretty well recognized that basically configuring the network independent of traffic, using intuition, and some kind of experimentation is not, let's say, going to scale. So how do we do traffic engineering? Well, we're going to have to integrate these three things: measurement, some sort of characterization of the traffic, and then setting up these knobs to best match the network resources to the traffic. What kind of time scale am I talking about? I'm not talking about something extremely dynamic, minutes to hours to capacity planning kind of time scales, months. Excuse me. So, typical applications, and there are others, are, troubleshooting performance. How come this link's congested? And I'll get into some of these later in the talk. The almost canonical example of traffic engineering is to do the intra-domain routing well. How should we set the OSPF weight to the ISIS weights? And, relating to the previous talks, how should I configure my BGP import policies, for example, to better share the load across the network. And then there's typical capacity planning, optimization kind of problems. Where should I put the next routers and higher speed links? So I'll consider these topics, and the focus of this talk is on the ISP backbone networks. So here's the typical task. By the way, there's a nice emerging IETF draft on traffic engineering by Dan Audouche. I don't know how to pronounce that, but it's and others, which I recommend to you. But here's a typical task. you'd like to have in your hands the topology of the network, the IP connectivity, and perhaps the layer 2 connectivity. You have some understanding of the demands, the expected loads between points in the network, for example, customers to various peering links, and vice versa. You have your set of knobs that you have to tune the network to meet those loads, and some sort of performance objective. So the question then is just, well, how do you set those knobs to get the best use of your facilities? Well, if you look at what we really have available today, the short answer is we don't have a topology at anything like the timescale needed to do this problem. We don't know the demands. The network doesn't adapt to the demands by itself, and the static routes are not necessarily optimized to the traffic. Other than that, everything's okay. So what's going on here is that these are not that people aren't configuring things correctly or something and aren't aware of this problem, but these are sort of symptoms of just the architecture of IP networks. They're decentralized. The global configuration is obtained by local configuration of individual boxes. They self-configure as connectionless, and interdomain traffic is huge, and we've heard all about that, and you don't have control over that. So let's look at another example. We have a congested link. Well, first you go through detecting that it's congested. There's various ways to do that. You have usually some sort of S&P polling going on. For example, you get utilization statistics every 5 minutes, or you have your active probing platform notify you that some delays have just jumped upwards, or you get phone calls to customer care, the customer's complaining. Okay, now what is the network provider going to do? Well, somehow it has to get to the root cause of why that link's congested. And there are just many different reasons, as you know. It could be some sort of natural thing. It could be just an increase in demand between a given set of source and destination pairs, or it could be that there was a failure in your network that caused the change in routes, or some other network had a policy change, the kind of thing that Tim just discussed. So how do you determine why the link is congested, and then what do you do about it? Well, so this is what we've been looking at, the longer answer to these questions. And this sort of describes the approach that we take and the systems that we've built that I'd like to describe to you. So first of all, we try to derive the topology of the network from the network configuration information. I may have a chance to discuss that further. We compute the traffic demands from edge measurements. That's a 2-hour talk. We have a module to model route path selection and route emulation in the network. I'll touch on that. And we have tools on top, query and visualization set of tools, other tools below actually also, and optimization tools even on top. And what we found, I guess, is that the same infrastructure for this kind of traffic engineering supports other processes as well. For example, configuration management, finding problems of misconfiguration. If just in trying to populate the model, you can uncover all kinds of things like that. Performance debugging, provisioning, a bunch of things. So I guess one of the takeaways I'd like to give you for this talk is that if you build this infrastructure, you can do a lot of stuff with it. So what does it look like? Well, here's the basic architecture diagram, and we take configuration information, forwarding tables, router config files, BGP tables, that kind of stuff, other kinds of configuration information, and parse it. That's the left-hand side model. We also take in various kinds of measurements, S&P measurements, Cisco NetFlow measurements, active probes, that kind of thing, and join that with the configuration net data, which is itself a puzzle sometimes, and use that to populate an information model, which I'll discuss a bit later. I drew this dotted line down here because I think it's important that you separate your monitoring, measurement, topology server, that kind of stuff from the information model itself, because things downstairs will change, and you don't want to change everything else above it if you can avoid it. Sometimes you can't avoid it. We also have a routing model that I'll talk about, and some stuff about visualization. So to go into these boxes a little more, this is what the configuration data looks like. We have we pretty much draw a circle around the backbone, and we want to know everything about the configuration, internal IP addresses, custom IP addresses, and external IP addresses in that cloud. In addition, we look at the layer 2 connectivity, for example, ATM PVCs. We want to extract the kind of information needed for traffic engineering, like the OSPF weights and reachability. And there are going to be some administrative policies, as was discussed in one of the panels, which aren't really in the configuration files, but you need stored there, and various conventions. From this, we populate this information model and get some unified views of the service, overlays on the service, customers, reachability, that kind of thing. There are two kinds of measurements that you'd like to use, I think: performance measurements and traffic demands. Performance measurements are widely available. They delay, loss, and throughput from some sort of active probing infrastructure end-to-end measurements, and also S&P utilization measurements that we're all familiar with from various tools out there, utilizations and so forth for links and nodes. One that is actually more of an open problem is the traffic demands themselves. So the performance gives you the effects of traffic demands. There was a lot of congestion somewhere, but really to do traffic engineering, you want visibility into the demands themselves. And you have to cope with the interdomain traffic. It's of course vital, and the fact that a large number of customers are multi-homed, and that or a large fraction of the bytes come from multi-homed customers. So we have some techniques that model the traffic demands, that collect edge measurements to come up with this traffic matrix. The point that I'd like to make here is that often you think of a traffic matrix as point-to-point, but that's not the right way, I think, to think about interdomain traffic, as you know, because there are multiple peering points that the traffic can take out of the network. So we think of traffic as coming from an edge interface to a set of candidate edge interfaces. That way, when we reconfigure the IGP, we don't change the traffic demands themselves. If you couple the two, if you look at point-to-point, then you will. And this provides a sound basis, I think, for modeling traffic demands. What does our information model look like? Well, routers, sets of routers in a node, the layer 2 connectivity, the traffic demands, that kind of thing. Not too surprising. And then what you need is some sort of technique for creating the right kinds of views easily and extracting data from your information model. You need to be able to select all different kinds of objects, for example, backbone edges or peering edges, or edges having some other property like being 60% over utilization or something. And this requires being able to map the statistics onto the network. And then it's also helpful to be able to generate various kinds of associated statistics. Another thing that we think is important, and is important for traffic engineering, is to be able to simulate path selection. And there's always going to be a trade-off between accuracy and simplicity. And there's always, just like there's always going to be a difference between what you read on the web page about how this path selection is supposed to work and how it works when you actually test it. And that's where some of the art comes in. And the only way to cope with that is to do testing and discover how these things work, and then decide how you ought to model them. This gives a view of the simple kind of view you can create with these systems. So you can map the utilization and delay onto the network topology and inspect it in various kinds of ways. So here I've mapped utilization, and red is high utilization, and yellow is low. And I've used the width of the length to indicate the delay. Okay, so you can sort of start to inspect how utilization and delay are coupled in your network. Okay. Routing. This just gives a simple view of the routing problem. You want to capture in ISIS or OSPF the selection of shortest paths to inform the multi-home customers and peers. X2, for example, is a peer here on the left-hand side. And you can see you can represent that graphically by having an extra node with two links into pseudo routers, if you will, which then connect into your backbone. So this gets into this point to multi-point modeling problem that I was talking about earlier. So it's vital to represent traffic flows between, let's say, peers and access links. This is just a little overly simplified view of the router simulator and how it works. It gives an idea of the trade-offs made in modeling for various purposes. So the way this works, the way we do this is we extract the backbone topology from the router config files and so forth, and the link weights from OSPF tables, compute the shortest path. We don't simulate all the bits and bytes that these guys have been talking about. We don't need that. And then, among the shortest paths, how do you split the load between them? And we basically emulate Cisco-style splitting without all the details. You could try to emulate all the details, but I don't recommend it. It's somewhat non-deterministic, and it's not needed for many purposes. But the basic idea is that it's an even split, and it works okay if you have a relatively large set of IP addresses being split by this technique. So it's recursive. So if half the traffic goes up and half goes down, and then the same thing happens at the next step, you'll get a quarter going up and a quarter going down. And you'll notice that the resulting path selection process doesn't give us it gives us a directed acyclic graph. Here's an example of use of that, and there really is no, I don't know what that is up there. We put a peering link up there at the edge of Canada, just conveniently put it there. But this shows what happens if you take measured demands coming into New York and ask, where will OSPF send those demands? They don't have to be measured demands. One of the nice things about a tool like this is, you might want to use forecasted demands, or you might want to use a different topology, and that should be just fine. But at any rate, it doesn't look like a tree here or a directed acyclic graph because of I'm not showing directions, but that's what it is. And so you can find, for example, that for this particular prefix being routed, a lot of it's going to Atlanta. And then you can start asking why, and is that what you intended? And that's the kind of activity that traffic engineering is all about. So let me review again what the basic systems needed are. You need a configuration management system. You have to have a way to construct the network topology from the local information, from the router config files or whatever technique you have. You're going to need a corresponding measurement platform which will integrate your active measurements, your passive measurements, your edge measurements, flow level edge measurements, for example. The point that I wanted to make here is that for traffic engineering and the internet, it makes sense to model traffic demands not as point-to-point, but point-to-multipoint. Then there's another rather large activity, creating the information model that you will populate from these data sets, routing. You can investigate various BGP choices or policies as well as IGPs, and then an environment to select query and support other things. One thing I'd like to point out is that there's a lot of opportunity for building tools above this kind of thing. For example, one paper that I sort of recommend people take a look at, I think you'll find it interesting, is this one about traffic engineering just by optimizing OSPF weights. There's been a lot of talk about the benefit of MPLS. MPLS really gives you surgical control over interdomain routing, so you can, in theory, route as well as the multi-commodity flow problem would allow you to think you can route in terms of load sharing. But how much better is that than looking at real topologies and real traffic than just well-designed OSPF? And if you look at recommendations that vendors have made for setting the IGP weights, they just have heuristics like use a weight inversely proportional to the link capacity. It works okay if you don't have anything else, but it has nothing to do with the traffic. Well, these guys, found that you can do a lot better with OSPF. It's not saying MPLS isn't important or anything like that, but it's very interesting, and it shows what you can do when you have this basis, when you have the topology and the data. Another sort of big activity you can support is configuration management, and another one is you can, create modules to do network reliability studies. Another one is reporting of various kinds. There are lots of different kinds of things to report to different kinds of people. You can build that on top of your databases. So just to sum up what we got here, a pretty simple idea that we take the data describing the network, all these, all this local data about hundreds and hundreds of interfaces and thousands of interfaces and so forth, and routing information and measurement information. We use that to populate models, various kinds. We do analysis, and we generate global views, which I've showed you a couple of them, of the impact of the traffic on the network. We went through a few iterations, and I think the components that I showed you, how to break this thing up into components to do traffic engineering are pretty well chosen, and show you that you need these separate systems organized as I described. And we've also found that you can evolve and change with the underlying infrastructure. Things are changing all the time. Line cards, software inside line cards, as you know, releases every 6 weeks. So you need the lower levels of the module to be flexible enough to keep pace with that. Finally, what traffic engineering ultimately tries to do is take this information and then better inform the configuration of the network, do better configuration, for example. And that's what we've been playing with and doing.
Questions yes, good.
This is a quick question from Albert.
Just now you mentioned that the traffic matrix, it's no good to have a point-to-point traffic matrix, say a router to router, because it will be affected by your interdomain routing.
Right.
Your intra-domain routing. So my first question would be, so what your traffic matrix looks like?
Yeah, we've got preliminary results on that, but I don't have them with me, and maybe we could talk about that offline. That's not only what does it look like, but what are the fluctuations? How does it vary in time? What are the heavy hitters? Do the heavy hitters move around? It's I don't have that with me. Sorry, but I can talk to you.
So let's see. My next question would be, say, just now you mentioned that from the first you measure the traffic demand at the edge, and then from the traffic demand at the edge, how do you construct the traffic matrix? Maybe we also have to look at
this. This is the long talk that I was trying to avoid. We use a combination of edge measurements, flow level edge measurements,
So
and
how do you-
reachability information.
How do you determine sync points from the edges?
We look at the forwarding tables, and we look at the customer IP addresses behind the prefixes in the BGP tables.
So you're running net flow on all your edges. You have these
No, not
massive
quite, not
distributed.
quite. No, but you're on the right, something like that. We can't afford to run NetFlow on every edge. Yeah.
I think I have another question is that, just now you mentioned that you have something to simulate the path selection. Is it shortest path?
Shortest path. What?
Yes,
Yes,
it's
right.
just like IS or OS.
Well, it's, yeah, it takes into account areas and things like that. So it's not strictly shortest path, but.
No constraint-based routing?
Oh, all right, no. Well, we have we have another, basically the IGP routing emulator isn't one thing, right? But the one I discussed is just the one just for shortest path. Yeah, you would like one for traffic engineering with MPLS.
Thank you.
Yeah.
Albert, so is there any alarm warning system that is inside the system that would alert the monitors to, hey, take a look at this part of the network, it is behaving strangely or badly,
Okay.
not working?
One thing I should say that this work is prototype systems, research systems, which are used by the traffic engineers to configure the network, but it's not operational in the sense of we don't have the data on a timely enough basis to say, but this is the vision that, okay, the link utilization just went up. So there are systems like that in AT&T, but not these. Okay.
Hi, I'm John Butler. I work for Mirth Splink. I was wondering how you implemented this, particularly the visualization tool.
Oh, okay. Well, go ahead.
What's it written in?
We tried to,
what systems you rely on?
we put a lot of work in the information model so that we could support a lot of different GUIs because people just like to have choice of GUI. The operations people might have some Java thing that they like.
Right.
We like Tickle. And so we tried to be agnostic and support multiple GUIs. A lot of people just like a list. They don't want a GUI. And it's important to provide people what they want. And iterate with the people that use the tool to find out what they want.
This is the last question.
Albert, are you taking into account any multiple busy hour type in the design phase or multiple time period aspects, or do you see or anticipate doing something like that?
Well, that's a great question. In that study that I mentioned by Nickel and company, they do try. They played with that kind of thing. They looked at, let's say, a evening set and tried to find and a day set and see if there's a universal set of weights, for example, that does well for both. But we just started. It hadn't really looked at.
So in your case, you are using a single traffic demand model. Is that essentially what it is then?
Yeah, basically there's some period over which you aggregate demands in time and also in space. And yeah, we looked at that snapshot. We didn't look at the dynamics in this.
Thanks.